Hello everyone, welcome to today's webinar from Swansea University. It's called Solving Global Problems Using Nanotechnology and Engineering Principles. For those of you joining us live, you can type in any questions that you've got for us throughout the session. On your display screen there, highlighted in the red box, you'll see your control panel. And if you use that Q&A button at any point, you can type in the questions that you've got for us. You can choose to send anonymously if you prefer. They will come through to us, and following the presentation, as part of our discussion, we will answer as many questions as we can, as fully as we can. So just to begin, if you're unfamiliar with the university, we're celebrating our 100th birthday this year. And it's grown massively in those 100 years. We've now got 2 campuses in the city of Swansea, which is a relatively small place. We've got just under 18,000 students, of which are just over 15% are from overseas, and a very large and diverse faculty and staff base as well. Now, within engineering, we've got a range of undergraduate programs. All have a year in industry or year abroad option, and are available with BEng, MEng or foundation year options across, as you can see on your screen, aerospace, chemical, civil, electronic and electrical, materials, mechanical and medical engineering subjects. And at postgraduate level, we've got a large range of taught MSc programs across those subjects that I've just mentioned, and then some more specialist MSc programs, such as engineering, leadership and management, or sustainable engineering, structural engineering, power engineering, virtual reality, nanoscience to nanotechnology, and computational engineering. And broadly, our research fits into 4 themes that you can see here. And we're going to discuss areas that sit into a couple of these today. So there's digital and computational, health, well-being and sport, water and energy, which is going to be a big focus today, and materials and manufacturing. And within the university and within the College of Engineering, we work with a large group of industry partners, some of which you can see on the screen there. So from big multinational companies to more local, smaller companies as well, on research, on student placements, on research projects at staff and student levels. Everything we do is applied. And that's the key thing, is applying the work and the research that our staff and students do into the real world, something that we're going to talk a lot more about today as well. Now, this has built up a fantastic reputation for engineering at Swansea University. So all of our engineering courses are in the top 15 in the UK, according to the Times Good University Guide of 2020. Our research quality is ranked 7th in the UK, according to the Complete University Guide 2021. And our research environment is ranked 2nd in the UK in the most recent Research Excellence Framework in 2014. And we're top 10 in the UK for graduate level employability, according to the Destinations of Levers of Higher Education survey. 97% of our engineering graduates are employed or in further study within 6 months of graduating. Now, following today's session, if you'd like to talk about engineering at Swansea University, about any of our programs or about studies, you can contact me directly. So my email address you should all have, and my WhatsApp number is on screen there as well. So feel free to stay in touch with me beyond today's webinar session. And without further ado, I'd like to introduce who we've got on the panel today. So my name's Adam, and I head up admissions and student recruitment for our engineering subjects at Swansea University. We're joined also by Dr. Alvin Orbaek White. If you want to tell us a little bit about yourself, Alvin.
Hello, everyone. My name is Dr. Alvin Orbaek White, but for brevity, you can call me Dr. Orb, and calling in from sunny Swansea.
And we got one of our current students, Abigail, who's joined us. So, Abby, do you want to tell us a little bit about yourself as well?
Hi, I'm Abigail. I'm soon to be a third year chemical engineer, and I'm just here to give you a bit about the student's perspective, what it's like at Swansea.
Brilliant. Right. So, Dr. Orb, I'll hand over to you then to run through the session today.
Well, welcome everyone. I'm going to share my screen very briefly with you, and we're going to have a little talk about solving global problems. So as I mentioned, my name is Dr. Alvin Orbaek White, but you can find me on Twitter at Dr. Orb. I'm a senior lecturer and I sit in the Energy Safety Research Institute, and we do research dealing with water, dealing with energy, and dealing with materials. Really, we think about the fact of energy security for a global security system in a future context. And that can mean quite a lot of things, okay? And I'm going to talk about a few of those things just now. I'd also like to give you a very brief update about who I am and where I've come from. So as a basic understanding, you can see that I come from Ireland. Maybe you can hear that in my accent. And I started my degree in Galway, which is on the west coast of Ireland. From there, I moved to France and I did a certificate in space studies at the International Space University. I've always been really interested in space studies. I love Star Trek and lots of other things like this. I'm inspired by what we can do on this planet and what we could do in other places. From there, I moved to Rice University, which is in Texas, in Houston in Texas, and I did a PhD in chemistry. So I did my degree originally in physics, and then I changed over to chemistry, and I found that extremely exhilarating. And then I moved to the Massachusetts Institute of Technology, where I did a postdoc inside the Department of Mechanical Engineering. So I've really gone from physics to chemistry to mechanical engineering. And now I'm in the Energy Safety Research Institute, and I'm in the portfolio of chemical engineering. And Abigail is one of my previous students from the chemical engineering portfolio from heat transfer that I teach here. I also want to point out a few other things about my background. As I mentioned, I'm really interested in space. This is a picture of me when I was at the Kennedy Space Center. I love to sail, and I've learned a lot about nature and about how to deal with problems and challenges. You know, you can't change the weather, but you can navigate the sail and you can try and get to calmer waters. And it's also taught me a lot about how to work with a team. We really got to work with a team, and we got to pull together globally to pull through some of the challenges that we have in the future. I also like to practice Aikido. It's a Japanese martial art. I'm a little bit out of training right now. It's been a long time. But one of the beautiful things about this martial art is it teaches you to center yourself, and it teaches you to get in the center of situations and allow all the flurry and all the negative energy to move around you, so you can move through life as best as you possibly can. I have a growing research group. I arrived a couple of years ago. I started out with my first postdoc, which is Nada here. I met her at MIT and I recruited her from there. And here we are in Rice University. That behind us right there is actually this is the Nobel Prize for Chemistry medal that was awarded to these two gentlemen. This is Rick Smalley and this is Bob Curl. We went on a trip sponsored by the connection between Swansea University and Texas Research. It's something that you could do when you come here. We've got a very strong connection with Texas, Texas A&M and Rice University and various other universities and hospitals over there. I like to have my research group meetings over lunch, over dinner. We like to break bread and to discuss things. And as you can see, we've got a diverse array of groups. I like to have lots of different opinions and have lots of different representation from all the different types of people in all the different places, to know where they come from. All right, so that's just a little bit about myself and about my research group and about the person that I am. So let me talk to you a little bit about where we're going from here, okay? As I mentioned, I did my PhD in Rice University, which is in Texas. And the thing about Rice University is that it's in oil country. And I learned a lot about the impact of fossil fuels. What I particularly learned is about how important they are for our energy infrastructure and how much we rely on them on a regular basis. And what I have here is a chart of the population of the world, all right? And you can see that it's pretty flat line up until around the year 0, and then we get to the year 2000, and then the number of people on this planet accelerates dramatically, and we're nearly at 8 billion people. And at almost the exact same time as this acceleration occurs, we start developing and utilizing fossil fuels, oil and gas. okay? And most of that oil and gas is being used for energy so that we can have the lights and the electricity and the internet like we expect right now. But some of the other fossil fuels, they become the materials that we use on a regular basis. One of those materials are plastics. And plastics are everywhere. Sometimes these plastics, you don't even recognize that they're plastics. They're like nylon, for example. Maybe you wouldn't consider that a plastic, but it's very much a plastic material. Now, this paper that I'm highlighting here has shown that there is 8,300 million metric tons of plastic that have ever been created, which is a number that's too large sometimes to fully understand and grapple with. I will just say that 60% of that material has been discarded. All right, so 60% of that material is in the atmosphere right now, in the environment and in the seas and oceans. And personally, that affects me. I don't think that's a very good place for it. I did a very quick calculation and I worked out that for every person on the planet, there is over 440 kilograms of waste per person. That's a huge amount of waste. So if you consider your individual responsibility to try and help clean the planet, that's approximately how much each individual person would have to do to do their part. And I intend to do that as much as I possibly can. The second thing to note is that in this case, recycling doesn't actually stop the material from going to waste, it just delays it. Okay, so we need to use another process is what I'm saying. The bottom line here is that everything that we have that we are used to using is all in this location. This is our home. This is our shared home. And this picture has always inspired me. This is one that came from the Apollo space astronauts. Okay, and the bottom line here is that there really is no planet B. There's no other place. This is it. So nothing gets thrown away. And we have a throwaway culture of we tend to throw things in the bin and maybe forget about where they go, not realizing that they're just going to stay here all the time. Okay, so what ends up happening is we end up building mountains of plastic. All right, we've got oceans that are swimming with plastic, and this is unsightly and unfortunate. So the big question is, how do we go from that position to here? How do we get to this moment in time? How do we get to this picture right here? Blue skies, blue seas. And this is the type of research and the type of ideologies that we have here at Swansea University with our engineering program and curriculum and our research. So what I propose here is a process called chemical recycling. And what you see here is a very simple scenario where someone is taking a bit of styrofoam, okay, white plastic, and they're dipping it into a solvent. And over time, that solvent is just dissolving plastic. And over time, as you can see in this video, the plastic is almost disappearing and it just goes into that solvent. So what I did is I developed a technology that takes that solvent, that liquid, and puts it into a furnace, okay? And when it goes into that furnace, then we can create carbon nanotubes, all right? Or we can do other types of material. We can make other types of materials if you choose. I choose to make carbon nanotubes. This furnace has got two stages. The first stage here turns it from a liquid to a vapor. And the second stage here turns it from a vapor to a solid. And we make this material over here, which is a carbon nanotube. Okay, this black material that comes out of the furnace is a carbon nanotube. And what's interesting about this is now the material conducts electricity. Before it didn't conduct any electricity at all, and now it's conducting electricity. So we're making an energy material out of a waste plastic product. To give you an idea of what these materials look like under a high-powered microscope, you can see here the white plastic material. When we use this, we make these long, fine, granular structures, similar with when we make the black polystyrene, use black polystyrene. This stuff I bought from the supermarket, for example. It was used to carry some meat that I had for dinner, and we're able to make it into these long, fine strands, as you see here. And you can see the morphology of all these materials are very, very similar, okay? And we see that when we do a test, we measure what's called the G to D ratio, all right? This is something to deal with spectroscopy, something that you'll deal with in your classes when you try to do quality assurance and quality analysis of your products. We see that the values all come up at 2. So the material doesn't lose any quality as a consequence of being made from black plastic or white plastic. So actually it's a beneficial material because we're getting carbon from a free source effectively. I want to show you another picture that comes from one of our high-powered microscopes that we have. Again, this is the black plastic material that you saw earlier. On the left here, you see a cartoon diagram of what these materials look like. And here you see this electron microscope image. It's called a transmission electron microscope image because it's as if the electrons are flying through the material. You can just about see there are lots of walls here, okay? And this is represented in this cartoon on the left-hand side. What I've done is I've taken this and expanded it quite a bit so you can see much better here. And here you should be able to see, if you follow the laser pointer, you should be able to see there are a lot of different lines here, okay? And that's because there are layers inside layers. Also, I've made some of the lines more clear by putting purple lines or pink lines along here as well. Now, I want to give you a quick understanding of scale so you understand what kind of size this material is. We've got a scale bar here for 5 nanometers, okay? And actually, I've discovered recently that the scale of a DNA molecule is roughly 2.3 nanometers. So each of those red lines is approximately 1 DNA molecule. So you can just see how small these materials are that we're able to use. We're able to image these and make these intentionally. Now you might ask, why make these materials? What's so important and special about these materials? Well, this is where nanotechnology comes into play. Okay, so first of all, I'm going to give an example of bulk silver. Okay, now bulk silver you're all familiar with. Hopefully you know that's where we get the name silver from. When you make silver at a smaller scale, at the nanometric scale, it actually has different colors because of its size, okay? So one important thing about nanotechnology is size. Size effects has a big consequence. The second thing is surface area is hugely important in nanotechnology. If you take a basketball, and this is an engineer's understanding of a basketball, sometimes we simplify things as much as possible, but basically this is a basketball, imagine, okay? And it's got a certain surface area, 0.18 meters squared. Well, if we imagine that exact same material broken down into smaller and smaller and smaller and smaller bits. So if we go from the macro bulk size scale that we're used to down to the nanoscale, the actual surface area increases to 1.7 million meters squared. So take that again. The surface area started out as 0.2 meters squared and then ends up as 1.7 million meters squared. It's the same amount of material, but it's much more surface area. And surface area is where chemistry happens. So when you can increase your surface area, you can increase the effectiveness of your process, okay? That's why nanotechnology is very, very important. The second thing, or the third thing, is what I call sorcery. It's a little bit of a play on words to have size, surface area, and sorcery. But really what I'm talking about is quantum mechanics. When you get down to the very, very small regime, materials don't behave in the way that we're used to, okay? They behave quite differently. So I'll give you an example. Carbon is a very traditional example of how things change at the nanoscale. As you know, plastics, they don't conduct electricity. They are often used to shield electricity wires. But when you take the carbon down to the nanometer scale, either as a fullerene or as a carbon nanotube here that I show on the right-hand side, this material conducts electricity now, just because it is down at the nanometer size scale. So this means we are able to make this material over here, like I showed earlier, and we can turn the lights on. And here I show, for example, the same type of fibers that you saw in the previous pictures. On the right-hand side, you see a moving image, and this is one of the devices that we have here on campus. This is a very special device. It's called a 2-point probe. And what it does is it holds one part down. This part is being held down, while the second part is moving along the wires and measuring the electrical conductivity. So we can do measurements on the bulk scale, where we can understand what the bulk material is like, and we can also understand it on the nanometric scale, how these materials perform. Now, that's all well and good and interesting for science, but in terms of engineering, it's more about application. So what I did then is I took this material and I put it into a cable, and what I'd like to share with you is a very brief part of a video that I created. So what you're seeing here are the black lines in the middle, okay? These black lines in the middle, they are actually carbon nanotubes, okay? And they are made from plastics. And when they are made from plastics, you can make them into carbon nanotubes, and then you can conduct electricity. And electricity is just like a signal. So you can transmit a signal from the audio device, from my computer, into a speaker setup. So what we used to have was a waste material, and what we did is we made it into a valuable material. And that's basically what I've been doing here at Swansea University. We're trying to turn problems into solutions, okay? And this is interesting to think about problems. I'm going to discuss this a little bit more down the line. Remember, we took fossil fuels, they were made into plastics. These plastics are waste, and what we did is we made them into a valuable material, all right? Not only is it valuable in terms of money, but it's valuable in terms of resource, that now this material can conduct electricity. We don't have to, for example, take copper or aluminium out of the soil, out of the ground from mining, for example. We could use this type of carbon to conduct electricity instead. I want to say something about responsible engineers and responsible engineering as well. There's something that I feel is highly appropriate and necessary, because there are a lot of tools out there that engineers have created, and there is a very strong responsibility that engineers have within society, because they tend to be the ones that solve the problems, or they're the ones who are brought in to do the problem solving, okay? My first point here is problems don't care about disciplines. As you notice from my history, I did physics, chemistry, chemical engineering, mechanical engineering, right? Problems need solutions. So you should open your mind to other perspectives and work with other people. Be good at working in teams. If you are not going to be interested in working on other types of backgrounds, that's okay. But respect other people's opinions about when they have a perspective on a certain problem or a certain issue. Problems need solutions. I've put 3 problems here: plastics, energy, COVID-19. These are all things that are going to be requiring lots of different backgrounds. So again, don't think about disciplines or subjects. Think about working towards solving problems, and things become a lot more intricate and complicated, but also a lot more fun. Then I'd also like you to think, do you have a real solution? Sometimes we have a tendency as engineers, sometimes we think, okay, I'm able to use a hammer, therefore every problem is a nail, and I go looking around for nails. Be careful with that approach, okay? I would suggest that it's good to recognize your skill set, but it's also very good to recognize whether people actually need a hammer. And if people don't need a hammer, don't use your skill set. Your skill set could be utilized somewhere else. Recognize and respect that. So some of the principles that I've used over my time as a research engineer, be observant. Some of the things I recognize were just in front of me all the time, but it took me some time to be observant and to recognize them. Appropriate technologies, just thinking about what is an appropriate technology. This is something that I teach in a master's course in Swansea. So if you stay for the master's, hopefully I'll get to see you there as well. We discuss a lot about whether technologies are even the answer sometimes. For example, in the case of COVID-19, one of the most appropriate methods to combat it is to wash your hands. That's not necessarily a technology, but it's a solution. So we think about these somewhat philosophical, but also practical questions to ask. And the last thing I'd have to say is you have to get used to being wrong, because most of the time you're going to be wrong, and that's okay. That's totally fine. So I salute you all for joining us today and taking the time out to consider your future and your education. I will close by saying, be an engineer, save the world.
Fantastic. Thanks for that, Alvin. Some really good scientific and technology content and applications, but also then systemic and human approaches to engineering, which is, as you say, key in solving some global problems there. So a reminder to the audience, if you've got any questions that you'd like to ask Dr. Rob, Abigail, or I know, you can type in your questions through that panel on your display screen there. I want to kick off by asking you then, Alvin, a couple of questions to begin with. You mentioned those 3 examples of global challenges that the world is facing right now. Are those the three keywords that you immediately see? Do you think that things are going to change going forward? What new problems do you see being presented? And what are your thoughts then on the main issues that we are facing currently?
Right, it's a really interesting question. I think right now I put those three up because they're the most immediate ones. I always think that whatever problem you want to solve, you're going to need energy to solve that problem. So if you want to have healthcare, then you're going to need to have some amount of energy to solve that healthcare problem. A lot of people have considered that education is an international crisis and we need better education, and I agree with that. So I would still say you need some amount of energy to have lights on, maybe to have give people access to the internet, and to tools and devices. You probably need some amount of energy, at least in the form of heating and cooling, to keep people safe. Some of the issues that are arising now are dealing with digital infrastructures. Artificial intelligence is a really big one. I think that students should be learning how to code like a second language as much as possible, because all over time, that's going to be the way that they're going to recycle devices and materials. Again, I would say that if you want to do any of those, you're still going to need some amount of energy in order to do that. So I still keep coming back to energy. So you can find energy is related to a lot of different challenges. And sometimes you will find that the challenge is really easy to identify, but now in the example of COVID, it has made it very, very clear that the challenge is not so easy to identify. Our traditional thinking of a virus and an illness and influenza aren't fitting with the data that is coming in. So data is understanding data, and data analysis is also a key challenge for students and engineers to consider.
Great. And if I'm a young 16, 17-year-old, as some of our audience are today, where do I go to solve this? Because again, your background is a really good example there, to have degrees in physics, chemistry, mechanical engineering, and now you're teaching in chemical engineering as well as some other subjects, this multidisciplinary approach. What would your advice be to students entering into higher education?
My advice has always been to any student who asks me this question, I always say this. I say, you have to go with whatever your heart sings to. You have to find that peace within inside yourself that really inspires you, really gets you up in the morning, and you have to follow that. At the start for me, it was physics, then it turned into chemistry, and then it turned into mechanical and chemical engineering. But I've always just been persistent about following my passion. I've been very fortunate and very blessed, and I recognize that quite a lot. I would also say, because I've seen some of the questions here about the interaction with the students and the staff, I have undergraduate students who are working in my research group from different time to time. At the moment, there aren't any right now. But one of the papers that I've recently published, one of the ones that I cited in this presentation, actually has the name Gemma Swan, who is a former undergraduate of the chemical engineering program. I'm always interested in working with students. The first thing that I say to students when they come to me, because they often I found personally when I started doing my degree, that it was very challenging to understand how it's all applied. And when I started working in the lab, I started to realize, that's why they teach us that in the classroom. So I think it's really important to have that opportunity to work in a lab. So I like to give that opportunity as best as I can to as many students as possible. But the first thing I say is, first you have to pass your tests. The first thing you have to do is you have to get through your class structure. Once you get through your class structure, we set up a meeting, we'll work from a distance, we'll work in the lab, we'll do whatever it takes. So to answer some of the questions, some of the students have been working in my lab. Some of the students, they chose other types of projects where they just did data mining and they did analysis like that. It depends on their particular skill sets. And I asked them again, always to consider to follow what their heart sings to.
So really nice follow on then, because I want to pull Abigail into this then. was it your childhood dream, Abigail, to be a chemical engineer, or like how did you find yourself on this path and what your background is? As the first part of my question, I got a little follow on to that as well then.
Oh, good. Well, I mean, I think for me, I was always just very fascinated by science and just had a curiosity for all those kinds of things. I constantly wanted to know why and understand how. And I think that led me down a lot of different scientific paths. Like I've always been very interested in physics, chemistry, maths, biology. And I kind of ended up in chemical engineering almost because I couldn't decide. For me, it married a lot of the different subject disciplines. It has chemistry, it has physics, it does touch on biology, it has a lot of maths, which I really enjoy doing. So for me, it was almost like I want to do everything.
You preempted what I was going to ask you. Is like when you've got in on the program, like is it quite blinkered, or do you touch and do you work across other sciences and engineering disciplines in their traditional sense, and with different types of people in your experiences so far?
I would say it is structured in so much. Sometimes people ask me whether they can go into different, like they can specialize within chemical engineering during the undergraduate degree. And I find that the undergraduate degree is really trying to make sure that you've got that solid basis and foundation, making sure that you know how to think like an engineer and you can use those tools and then apply them, get more specific later on. But there's been lots of different opportunities to kind of explore different interests. One of the things that that the engineering department do is invent for the planet. And it was really interesting seeing your presentation, because what I did was the plastic oceans and trying to come up with some sort of solution for how much we're dumping into the oceans. And it's really interesting because one of the problems that we came up against when we were doing that, we kind of came up with a collection method to kind of target the rivers that a lot of the plastic was coming out of, but we were like, well, we don't really know what to do with it once we've collected it. So it's really interesting seeing this, because we're like, aha, look, there's there's what we could do with it. So it's really interesting seeing all these different things coming together and all these different ideas from multidisciplinary backgrounds. And that is what Invent for the Planet is. You just come together with loads of different types of engineers, and it was really good working with different engineering disciplines and seeing what their strengths and weaknesses were.
Great. You've mentioned something there that I want to touch on. You said, think like an engineer. What is an engineer and how do they think? Because it's something different for every person you'd ask, isn't it? And there are stereotypes associated with that. And in some cases, there are negative connotations attached to what an engineer looks like, sounds like, thinks like. That's just born out of history and these historic perceptions of that. Now, through the typical historic way of looking at engineers, Abigail, I'd say that you're a non-typical engineer, but that's why we need to rewrite this definition of what an engineer is, isn't it? So tell us, what are you like outside of university? I know you're part of certain societies and clubs. What are your interests and what sort of person are you?
I would say one of the biggest misconceptions that I feel like I've been to is that we're sort of it's like purely academic, and there's kind of, we want facts, figures, and I think there's a lot of room for creativity. I mean, it might be a different kind of creativity than creating, an art piece, but I think at the heart of engineering is problem solving. We're problem solvers, and we not only want to know why, but we want to know, well, how can I make that work? How can I change things? So I think there's this idea that like, it's all very like just the books and it's just maths, and there's no room for like, oh, but what if we tried this? Or what if we tried this? Like creativity I think is a big part of it. And that was one of the reasons I went into engineering, is because I wanted part of that creativity and part of that problem solving.
Spot on. And I know, Alvin, you've got thoughts on this as well, because you've touched on how engineering solving these problems You know, you can't be a certain subject or a certain discipline or subject area. And it's similar to people. You can't be a certain person that can only solve certain types of problems. You need this variety and diversity and interaction between different types of people. So what are your thoughts on that, Alvin?
Right, it's a great question, and thanks for your input, Abigail, on that. I would say I would second what Abigail has said, but I'd add a few other things because I've come from a traditional science background of having done a first physics and then a PhD in chemistry. Scientists have a tendency to want to know the exact reason why something has occurred, and they're very stubborn about finding that out. Engineers are okay with the first guess or the second guess, and they'll just build from there on. So I think one of the downsides of engineering is sometimes they're building something that they're not fully respective of what the consequences might be. And that's why I teach in the master's course and the more about responsible engineering and about appropriate technologies to take a step back and recognize, is this the appropriate thing to do right now? The good thing about that approach is if you have an engineer on your team, you can almost be sure that by the end of the project is over, something will be built. You will have some answer somehow. And the creativity is one of the things that I really appreciate with engineers and how they put things together. They're very much problem solvers. They solve problems on different levels. Some of them are very good mathematically. Some of them are very good with their hands on. One of the things you have to recognize about an engineer is engineers span from a tire mechanic to a brain surgeon. So it's that there's that full line of potential still has the technical term of an engineer.
Great. We've had some brilliant questions that have come in, so I want to turn to some audience questions and bring it back to some of the technical aspects of your work then, Alvin. So the first one is to do with the chemical recycling and the development of nanotubes. Is there much waste that's produced with that? And if so, what happens to it?
It's a great question. I love that question. Every time I've been to Westminster, I get asked that question and one other one. So is there much waste? Unfortunately, the process isn't 100% efficient right now. So we don't make 100% carbon nanotubes from 100% of the carbon that comes from the plastic. And so one of the aspects that we're working on in the future now, actually right now, is to increase that efficiency. And that's something actually that you'll find, my science side is understanding the exact mechanism by which this occurs. And my engineering side is finding out how to increase the efficiency.
Yeah, I would just say it's funny because when I was watching your presentation, there was a part of me going like, how's that going to work in a process? Like, what do the materials need? What's the manufacturing time? How much would you need? So there's already the sort of problem solving cogs going round trying to make it, a product.
Brilliant.
But I suppose it's sometimes the difference between science and engineering.
Yeah, and actually I'm working on this now. I've set up a company that is trying to spin this out and make this into a commercial process.
Oh, wow.
Great. Okay. Looking at nanocarbon, whether it's carbon nanotubes or the waste associated with this, alternative uses for it. We've spoken about how it can conduct, whether it's electricity and signals. So we've got a specific question: can it be used and put into concrete or replace steel? First of all, Alvin.
Right. I don't think it's going to replace steel. It doesn't have the same type of mechanical properties as steel. The steel is very, very rigid, and carbon nanotubes are very, very flexible. Although carbon nanotubes have a much stronger tensile strength compared to steel. I think steel has a tensile strength of about 1,000 gigapascals, and carbon nanotubes have a tensile strength about I think 10,000 gigapascals. It's orders of magnitude improvement. It's just not as rigid. So it's not going to replace steel in that same way. You're still going to need steel girders, but it can be added to concrete. And there are some groups that have added it to concrete, and they made the concrete slightly electrically conductive. And they made it enough conductive that you can put it into a bridge, and whenever the bridge or the building moves from side to side, it squeezes the bricks. And when it squeezes the bricks, it changes the conductivity. And when it changes the conductivity, they can measure how much flexure the building has undergone. So they can understand the aging of the building with time.
And what other sort of alternative uses do you see going forward with these as well?
The big ones that I see are anywhere that you want lightweight, high surface area, and you want to employ the different effects of the nanomaterials compared with the bulk. So historically, we've already been using, since ancient times, we've used charcoal to clean water and use it as a water filter. So carbon nanotubes are another form of carbon, just like charcoal, and they can be activated just like charcoal. So you can have very, very fine water filters and other types of filters. So you could separate oil and water, for example. So you could use it for that type of process. You can use it in electronics. That's one of the places that I'm really excited about, because you can make transistors potentially much smaller. At the moment, the smallest gate of a transistor is 20 nanometers. Whereas a carbon nanotube is 2 nanometers in diameter. So you could make a transistor 10 times smaller again. The one that I'm really excited about most is to conduct long-range electricity using carbon nanotubes, mainly because it is very, very lightweight. Its thermal properties are beneficial. It doesn't heat up when it's undergoing conduction, and if it does heat up, its thermal conductivity is about 4,000 compared to 400 of copper. So it's able to dissipate its heat much better. So you could have cables underground as well as above ground, and the ones that are above ground will have a lot less sag and mechanical pressure on the pylons, because the material is much lighter. So you have a number of these consequences that you think about as you go down the line. You could have them in electric vehicles, because electric vehicles have motors on each wheel, and the motor has got copper cable inside them. And if you use carbon, which is 1/6 the density of copper, you make those motors much lighter. Therefore, you can make the efficiency much higher on an electric vehicle. And we're just tipping the ice. We're just touching on the tip of the iceberg now, but there's plenty of different applications I foresee.
Brilliant. There's a question that's come in, I think relates more to the process, which Abigail was touching on there as well. So in terms of chemical recycling, is there a large-scale solution? And specific to your work, can it be done in bulk and en masse, and to what extent with plastics?
Yeah, that's a great question. I get asked that quite a lot as well. That's the second question that I get asked. Yes, my answer is yes, it can be done. The technology that I've developed incorporates or utilizes off-the-shelf manufacturing techniques. The background research that we have done, that I've done, and my colleagues have done so far, suggests that it can be done. It just requires some amount of investment to actually do it. There is, to speak generally about chemical recycling, I wrote an article in The Conversation about chemical recycling. So if anybody is interested in it, there's a very user-friendly article there. Look for my name on theconversation.com. There are multiple processes that many different companies are using to use this philosophy of chemical recycling. And some of them are doing it on bulk scale of tons a week and tons a month. And my particular process, we're aiming for about 1 ton a month of conversion.
Okay. Another couple of questions specific to carbon nanotubes, Alvin. Can they transfer data? And if so, how quick? And could you one day see them replacing like fiber optic cables, for example? So
whoever asked that question, I'm just after buying an RJ45 crimping tool, because I'm going to make a Cat5 digital cable at home while I'm working from home. And I'm going to use, basically going to make my own digital broadband communication network at home using these data cables. So to that person who asked that question, come work in my research group, because I like your questions. And my answer is yes, I believe it can. What the exact parameters are, what the bandwidth will be, and what the baud rate will be still has to be determined.
Great, and I love that in lieu of getting into labs at the moment, you just experiment in a home with your home system there.
Yeah, sure. That's all that's my whiteboard that I built for myself at home, and I'm just doing a lot of just working from home.
Right. In terms of implementing them in today's energy systems, how efficient have you managed to get it? And specifically, are nanotubes better than graphene or gallium nitride circuits? Can they improve current batteries?
Oh, that's a great question. There's 3 questions there. let's start with, are they better? I don't know that anything is better than anything else. Okay, I think some people have a tendency to say that my technology is better than your technology. I don't think that's a fair assessment, because again, it comes back to this point about appropriate technologies. I would say, where is the technology most appropriately used? Okay, so gallium arsenide has been very appropriately used for a long period of time to make a lot of digital technologies possible. And I think it's probably in some cases the more appropriate technology in some applications. Carbon nanotubes are probably going to be more appropriate when you want lightweight, because carbon is so much less dense than metals. Is it better than graphene? Again, it's going to depend on the appropriateness of the application. So in the case of electrical conduction, they are sometimes similar, depending on whose reports you tend to believe and what way you set up your experiment. But in terms of strength, nanotubes are a little bit better because they're actually longer, whereas they're much longer and they intermingle much better, so they make much higher tensile strength fabrics. Whereas graphene has a challenge that it slips on top of each other quite a lot. Then in terms of actual manufacture, you can make nanotubes now. The industrial quantity of nanotubes being made globally is on the order of hundreds of tons a year. Whereas with graphene, I think they're still working on silicon wafer scale. So in terms of appropriateness, in terms of accessibility, I would say nanotubes are more appropriate.
Okay. In this specific example, you spoke about you using polystyrene and especially the black plastics there. Can any other plastics be used in your process? And does it affect efficiency or anything like that?
Oh, I love that question. Efficiency. We have a natural born engineer right there. Okay. Let's say my short answer is this: yes and no. Yes, lots of different plastics have been used. I've used polypropylene, polyethylene, polyethylene terephthalate, polyvinyl chloride, nylon, woven fabrics. I'm not going to remember them all now. And I've used them in a way, or we've used them in a way that they've been all melded together. So we've used a product that comes to us that have got between 20 and 40 different layers of different types of plastics, and we've been able to convert that. This example that I showed to you now with the polystyrene is the one that we've published, and it was a test case scenario that we used. And when you use a singular input, the output is much easier to determine. When you start to input lots of different types of plastics, it's more challenging as a scientist to ratify the effect of the different parts and to really understand what the efficiency is. But as an engineer, we think more about the mass balance of carbon entering and the mass balance of carbon that's exiting. And the efficiency at the moment is on the order of magnitude, maybe 10%, depending on the way that we look at it. And of course, we want to increase that as much as possible. So I'm looking at approaches for doing that that include different types of techniques for making carbon nanomaterials and so forth.
We've had a few general study related questions come in. So Abigail, there's a few here that you can answer, and I've got a few answers for some as well. I'll ask the first one verbatim and explicitly. Do females ever feel intimidated by taking engineering subjects, due to the fact they do seem quite male dominated? So what's your sort of thoughts and experiences with that, Abigail?
I suppose I remember the first time I ever stepped into any sort of university. It was actually Bristol University, and I was 14. And I was going around as a work experience. And I do remember the first day kind of thinking, no one's going to take me seriously. And indeed, I was a 14-year-old kid, but there's also this idea of, I know that I'm not the stereotypical type of engineer. I'm not the stereotypical type of scientist. And there is that fear of not being taken seriously, or feeling like you need to work harder to be taken seriously. But I would say what I found, especially as you move higher up in education, what is really respected is passion. I think among academics, even when I was 14, going around the astrophysics department at Bristol University, if it's your passion, if it's what really sparks you, what drives you, as Dr. Orb was saying, if it if it's what motivates you, that's, I find, what a lot of academics respect. I can't say that at university I've felt too much the difference, or I felt intimidated. And I think sometimes that kind of things that maybe I experienced a little bit in sixth form, with people going like, well, this isn't a girl's subject, kind of almost gets whittled out as you move higher up in education, and people really just start to respect, your knowledge, your passion, your dedication. And
I know within the department, there are formal ways and informal ways to navigate, studies as a woman. So we've got the Women in Engineering Society.
It's a really, really nice society, actually. Yeah.
Yeah, but then it happens organically and informally with you amongst your cohort and as the student body as well, which is nice to hear as well. Another question came in for you, Abigail. What's been the most challenging part of your degree so far?
Ooh, interesting. I mean, I think that's going to be different for everybody. But mine personally might be more like time management. I get a lot of questions saying, is engineering difficult? And it's difficult because, yes, of course, it's going to be a bit more of a challenging degree. I've found that, like, if it really is what you enjoy, if it really is what you love, there's going to be dull bits, there's going to be really, really exciting bits. But I think the most important thing is passion. But I mean, most difficult thing, maybe workload, but it's made easier when you're really interested in what you're doing.
And a lot of people, we've had a few questions come in, so I'm trying to answer about 4 or 5 questions in one go here now, because there's a lot of people who are maybe uncertain about what engineering subject or discipline they want to study as an undergraduate, or they want to know the differences between certain ones. So obviously there are similarities between some subjects for a bulk of their modules. So I know the chemical and materials science and engineering share quite a bit of like the chemistry related ones, and there's sort of, and then there's mechanical and aerospace engineering, which are quite similar. But to be fair, you could have a mechanical engineering student, an electronic and electrical engineering student, a chemical engineering student, and a material science engineering student all go and work in the energy sector at the same company, working on the same project. So a key thing to get across is, yes, the sciences and the technology and the sort of even the maths in some cases varies from subject to subject, but then it's how you apply those sciences and that maths, isn't it? It's the impact that you make is where, as Alvin was saying, subjects don't exist anymore in effect. So you can go into a range of subjects and still end up working in the aerospace sector or in energy or in oil and gas and whatever it may be, because as Alvin was saying, it's that wide range of knowledge base and person that is needed on projects in certain fields and sectors. So I know, Abigail, you've got like have you worked with other engineers? You mentioned the Invent for the Planet project, and where do you want to go beyond your degree? What sort of sector do you want to be working in? Do you know yet?
I feel like with chemical engineering, it's almost a bit like you're spoiled for choice, because there's quite a lot of sectors that will employ, especially chemical engineers, but all types of engineering, you can go into lots of different things. I am especially interested in sustainability and environmental engineering, and I think that's probably where I want to take my degree and what I want to do with it when I graduate. But in terms of sort of answering what type of engineering, I really think just do a bit more research into it. Like you can look at the syllabuses that we have online, the engineering handbooks. You can look at what they do for a living. And again, back to what I said, really, I think it's just about what really excites you. What, if you kind of look at a subject, you go like, oh, I really want to learn more than that engineering.
There is a lot of resource out there. I know there's a lot on our website about explaining as a whole, what these disciplines are and where they are applied, and specific levels to your modules and your topics and subjects. There's a couple of questions about whether students can change their degree program, and typically not. Once you start year 1 of a program, you are on that engineering program throughout your degree. That's the key thing I was trying to get across, is that, you know, you can still go from an engineering discipline and a subject and work in a wide range of sectors and apply that differently. Alvin's a good example, who has gone from, you know, certain subject areas across postgraduate degrees and postdoctoral degrees as well. So you're not boxed in to a discipline once you start, for example, a chemical engineering undergraduate degree. So I do hope that helps a little bit. A couple more technical questions back to you then, Alvin, because we had loads of questions come in about your work. Do you think the carbon nanotubes may have an unexpected negative impact on the environment, like Teflon or forever chemicals, as the example that's been used in question?
That's the third question that I usually get when I speak with policymakers and politicians. So it's a brilliant question, whoever asked that. Thank you very much. And something that I consider very deeply. And it's part of the emphasis that I use when it's part of the philosophy that I build when I create the coursework for the appropriate technologies course. You can never know what to unexpect. That's the nature of the unexpected. But you can try to work in advance to mitigate or lower down any damage or any consequences that might occur as soon as you discover them. So what I've done already is I've started working with scientists in the biology department, and we've started to work on animal studies to see if there's any toxicological effects of these materials on any animals in the ecosystem. So I'm very much interested in understanding whether there is or there aren't. So far, it's mixed results. Some of the animals don't get affected by it at all. They ingest it and then they just let it back out. Other animals get affected by it when it's in their system, but once they release it once they get some other food, then they don't get affected by it. So it doesn't seem to be a deal breaker at the moment. And I think it's an excellent question, and it's something that I'm going to keep my finger on the pulse as much as possible. And when as part of the interdisciplinary nature of the research that I like to do, I'd like to look for colleagues in the biological sciences, in toxicology, nanotechnology, to try and understand that as much as possible. There is a thing called life cycle analysis, and I'm putting in an application for a master's student. I don't know if I'll get to receive the funding, but that's exactly the kind of thing that we'd be studying, is to do the life cycle analysis, do a technical analysis of starting with the carbon atom coming out of the ground as oil, turning into the whatever plastic, turning into the nanotube, and then understanding how far could it last and survive. And so I don't have a definite answer. I just have an approach.
Great. I know you've got an answer to this next question because I'm familiar with your work already. So you've spoken about the high tensile strength of carbon nanotubes. Can they be used in the future of space, such as with a space elevator? So I've seen your eyes lit up now already because you've got a lot to talk about with this.
So I'll answer two questions here. First, the thing about being boxed in with different engineering. You don't get boxed in with engineering. Only you have to do certain specific subjects. But after that, you go on and you do whatever you want in terms of your job. And I'll give you an example from my life. I did my degree in physics. I ended up working for a company that was building a space hotel. So I was hired in as a junior engineer to work on that. So I have a lot of interest in the space industry. Yes, I think the carbon nanotubes could be utilized as a space elevator material. That was the predicted type of material in the original book, Fountains of Youth, that it would be a diamond-like material, which is what carbon nanotubes are. Whether we should make a space elevator or not is a question I also ask, and I'm not sure that we should. I don't know that we should necessarily have one on planet Earth. Maybe we should. Maybe we could use it on other planets. I'm not really sure. But technically, yes, it could be the material that we could use. I've also seen someone mention something about avionics. Yes, I believe carbon nanotubes could be a benefit there because, again, they're far less dense. That means their weight, their mass is much less compared with metals. So going to space is very, very expensive. So any mass savings that you can create as a consequence of your material choice is a benefit.
Great. Are nanotubes, obviously they're derived from a recycled material. Are they then recyclable again once they're made, or is that structure permanent? This is an excellent question. I'm curious for this answer.
This is a great question. They are restructurable. You can remake them into other materials. So let's say, for example, if we didn't use them for anything, we didn't use them for conducting electricity, we didn't use them for space elevators, but we just took all the excess carbon dioxide in the atmosphere and squished it down into a carbon nanotube, we'd probably be able to fit all the excess carbon into a small house, because we get that nano effect that we squish everything down. So we could do that. But if we wanted to use that carbon later, for example, we wanted to use them in the pharmaceutical industry, we wanted to make different types of compounds that we require, we can still do that. Nothing is permanent. So chemistry is all about change. Nothing is permanent.
Okay, we had another good question that came in. Oh, to be fair, all of these have been good. You think the nanotubes have properties in which they can be used inside the body or medically? So, for example, to treat nerve damage, using the nanotubes as conductive properties to replace nerves?
People have been working on this for a while. I don't think they've been able to succeed in actually replacing nerves yet, but they did actually find out that you can grow nerves on top of nanotubes. So if you put nanotubes in and you put nerve cells around it, they can grow around it and they can actually interact with the nanotubes in the circuit. It's really interesting work. I don't think that's ever gone into into anybody's head just yet, but technically the electrons can transfer from one to the other and there can be electrical communication between the two. In terms of work that has been done, I was part of a study that was using carbon nanotubes to treat cancer, and we were injecting the nanotubes into pig bodies, and then they would arrive at the cancer cells, connect via antibody connections, and then you would heat them up using radio waves, and then they would ablate the cancer cells. So there's some ways that they were being used, and in other ways, in terms of the electrics again, there is a group, I don't know if they ever published this, but I did used to work with them. They were making very, 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 very fine wires. Presently, at the moment, the current standard is to use a titanium, I think it was a platinum wire, sorry, but platinum is very, very expensive. And you use a platinum wire to go inside and get into the heart, and you kind of like scorch it in certain little locations. Well, they decided that they would start using carbon nanotubes instead, because then the scorch pattern could be much more finer and they can do little incisions and do little work like that. But so that's kind of working in the vein of what the person was asking about.
Good. We have a couple more questions about alternative uses as well. So could carbon nanotubes be of use in the aerospace industry? Replacing copper wiring using avionics, for example. I know you've touched on wiring already, and it's just applied in this different sense then, isn't it?
Yeah. So to put it into perspective, I think in a general, like in a in your average airplane, there's something like 30 or 40 kilometers of cabling. All right. And if you ever go on those long distance flights and you've got a heads up display in front of you and everyone has their own TV, there's even more cabling inside that, because that all has to be fed with signals from a mainframe computer on board, and it has to be fed with power. On planes, they don't tend to use copper anymore because copper is too heavy. So they have a mixture of tin and aluminium and a little bit of copper. So they actually have less conductivity, but they afford the less conductivity because they have lighter weight, and then it makes it easier for the planes to fly. So there is definitely an application for carbon nanotubes in the future, certainly.
There's one that's come in. Could they be used in warfare, such as with tipped bullets or missiles?
I don't know that they would give any benefit in the tipped bullets, honestly. I have a friend who specialized in making armor with carbon nanotubes. They actually put them into, and then a colleague I know put them into helmets and was able to save, they showed that the fact that the carbon nanotubes were in the helmets was able to save the soldiers' lives because it helped with the impact.
And then could it lead to the production or creation of nanobots?
Well, I'll have to admit, like when I started this all out, this is one of the things that I was most intrigued about. There's a wonderful book called The Engines of Creation. If you haven't read it yet, and you're interested in this kind of thing, I suggest you go and read it now, The Engines of Creation. It's very fanciful. The guy did his PhD in MIT and wrote a very large book, which is now in my office in Esri. I bought as well, talking about the mechanics of how these things would actually work. Drexler. Yes, I think that carbon nanotubes could be. I don't think carbon nanotubes on their own would be utilized. Again, it's a question of appropriateness. What has been done in the past is people have made little cars where they actually use fullerenes. So if you remember, I showed the carbon nanotubes on the bottom of the screen, and I showed the fullerenes. They're like the football buckyballs that are on the top. They were used as wheels, and they actually had a chromophoric material which responds. Chromo is just light; it responds to light. So whenever you shine light on it, the molecule rotated, and it was connected to a drive shaft, and the drive shaft were connected to the wheels, and the wheels turned and the whole thing moved. And so there was a competition about 5 years ago for making the nano car, and they were basically shining light on a small little surface and looking at it with a microscope to see which nanobot made it across the line fastest. So I think definitely they could contribute to the engineering and science of nanobots, definitely.
I've got one more really specific technical question. Could carbon nanotubes help the progress to a room temperature superconductor?
Well, if you solve that one, we're going to have a Nobel Prize. Superconductor is a very specific physical term, all right? So it's not just that it's a good conductor. A superconductor means that there are pairs of electrons that are traveling simultaneously beside each other. And in order for electrons to get close to each other, basically electrons don't tend to travel with each other very much. They try to be as far away from each other as much as possible. And that usually occurs, you can get them to be close to each other at very, very low temperatures. There are some reports that suggest that actually the way that electricity conducts in carbon nanotubes is by electron pairs. So there is some suggestion in the literature that they are already superconductors, but this is something that hasn't been ratified with the rest of the scientific community. So if it is, then it's already answered that question to say that it already has developed low temperature or room temperature superconductors. And if it isn't, then the search is still on.
Abigail, there's a question back to you. So for chemical engineering studies, how much practical work is there compared to theoretical work? If you want to start from how it's changed in dynamic from year one throughout as well.
Yeah, I mean, I think as with any engineering discipline, you want to be able to see learn the theory, but then see how it's applied in practice. Engineers are very much about coming up with solutions. They want a product at the end of it. So I think it's really important seeing the translation. For chemical engineering, I know that first year we'll do chemical labs, and that is a bit more, like your A-level chemistry. They really want to make sure that you have a good foundation in a chemical lab. Just also, like when you're in industry, what your chemists are talking about, because you'll be working in a multidisciplinary. Second year, it really tries to focus on teamwork, but also more on, you'll be in pilot plant labs. So they're like huge labs with these different bits of equipment, like distillation columns or heat exchangers, or we've got a partially permeable membrane that cleans salt water. So what they try and do is they'll take a theory from your lectures, and then they'll throw you into the labs, and you'll be able to see that actually applied to the real equipment. So in terms of a split, I don't know, it's difficult. I suppose there will be weeks where you'll have pretty much all theoretical or in your lectures, but there's also going to be weeks where you're running about madly in a lab trying to get all of your research done on time and be able to write up all of your different bits of data so you can do a really good lab report. I quite like the balance.
Yeah, and it changes semester to semester and year on year, and even then the practical activities become different, the theoretical activities and lessons become different to, 300 in a lecture theatre. It's always changing. We were speaking before the show about your design project next year, Abigail, and so what's that going to involve, and what will you be doing with that?
So third year is the only year where you're not really in labs that much. But what the design project is they'll put us with, a few, I'm not quite sure the numbers, but a few members of our peers, and they'll set us on a sort of real world design project. So, we'll be having to produce a certain amount of this particular material, and we'll have to be able to justify it from beginning to end, where are we sourcing it? What is this process going to look like? How efficient is it? Designing all of the different parts of the process. And it's a really huge challenge, but it's also a really good a teamwork experience, you're again, you're kind of leaning on each other and trying to take in everybody's strengths and weaknesses to produce a really good end product. And I think it's quite an employable skill, it's a very challenging teamwork experience, but it's good to then take forth into the real world.
Yeah. And then a couple of questions came in, Alvin, about how students can become involved with projects that have real world application and collaboration.
Ask the professors who are in charge if they'll take you on. Okay, that's number one. So go and have a look at the different professors who are involved in research and see which of their research you really engage with, that you really like. Again, I would suggest that you do the thing of following what your heart sings to. Any research that you do with a professor doesn't have to be permanent. You don't have to stay there forever. It could just be for a semester or two or something like that. But here's where the balance becomes. It takes a certain amount of time to train a new person when they come into a team. So as someone with experience who constantly takes new people into the team, I always have to balance, well, how long is it going to take me to train this new person, and how long are they going to stay afterwards? So one of the questions I ask is, how much time can you actually dedicate to this? And here's the caveat. I always say the first thing you are here to do when you're in school is to pass your exams. All right. So, and I would help them if they need extra help with certain things. We can find them a study space, or I could be like someone that I could mentor them through certain things. But that's the number one priority when you're in school. All right. When you get to research stage, when you're doing a PhD and a postdoc and a master's, is a little bit different. But as an undergrad, the first number one thing is to do that. But if you're able to handle your exams and you have enough extra time and energy and interest, then know the person who you want to reach out to. And you have to actually kind of decide how you're going to approach them. And one of the things I would say is you need to approach them in a way that you show to them what you are going to bring to that team. I call this, in other words, managing up, because as a perspective of a professor, I'm going to be looking at this person thinking, how much time is going to be dedicated to train this person? Because that time is taking away from some of my other students or some of the other work that I need to get done. So you need to show to that professor that what contribution you're going to make. Okay, because that helps them understand the balance. It's also a very mature thing to think about as well. Especially, it's almost like a job interview. It's a mini job interview, because we don't have a system where it's required for you to do research, or we don't have a system where you'll get extra credit for doing research. So you're only going to be doing research for your own benefit on your own time. And the professor who takes you on is only going to get credit. They're not going to get credit. Sorry, it's only a benefit to the person who's going to get the research experience, because unless you stay for 3 or 4 years to become a really proficient user of a certain device, like in the case of this undergrad who worked in my lab, she came for 6 weeks. I taught her a very specific piece of software, and I said, learn that software to do this exact task, because I knew in the future I needed someone with those skills. I think about it like a football team or a sports team. I need a goalkeeper, I need a striker, I need people in different positions. And she did exactly what I required her to do. And then when that skill set was required, she was there. And so she got her name on the papers. And that's the kind of thing that if and that's the kind of way that I would suggest. That's how I manage it. Other people will manage. So that's where you have to start with understanding who you're going to go and connect with.
I think the best thing that we can do is provide this, as you said, this good curriculum, this good education that touches on so many different areas of science and technology that can then be applied when the time is right, you know, beyond the completion of degree program, where you enter the real world and you've got the tools and the knowledge and the network in some cases to then go in and narrow in on something specific that somebody wants to be working on. You need that broad base, first of all, isn't it?
Yeah.
Brilliant. Right. That's all that we got time for. I know that we have some questions that haven't been answered. I wondered, Alvin, before we go, if you put up your first slide, it's got your contact details, your Twitter handle, that people can get in touch with.
Sure.
Thank you to everyone for joining us today. You can look on our website, it's swansea.ac.uk, and you can search for Alvin, you can search for our Energy Safety Research Institute or carbon nanotubes, and there's a lot of good resource that's on there. You can contact me directly, or you can contact Alvin directly if you've got specific carbon nanotube related questions. If you want to talk about your studies, you've all got my email address and you can contact me at any time as well. Great. Abigail, thank you so much for joining us today. It's great to have your insights and thoughts as a current student going through this pathway, working towards something.
Yeah,
Alvin,
it's been really great to be here and hear about all of this.
Brilliant. And Alvin, thank you so much for your time today and about that great work that you are doing.
Cheers.
No
Good
worries.
luck, everyone.
Thanks, everyone. Have a good day.